Hi Bobcats. This video is going to take a look at several examples of drawing Lewis dot structures. As I work through these examples, if I start going too fast, just pause the video and make sure that you can keep up with what I'm doing step by step. You may need to rewind it to see exactly what I did. This video also is going to focus only on compounds that follow the octet rule. Later videos are going to focus on ones that are exceptions to the octet rule. Our first example is water, H2O. If you look at the periodic table, hydrogen is in group 1, so it's going to have 1 valence electron. So if we're going to count valence electrons for this compound, we're going to have 1 valence electron from the hydrogens, but I'm going to multiply this by 2 because we have 2 hydrogen atoms. That's what that subscript means. Then the lack of a subscript on oxygen means that there's just a single oxygen atom, and if we find oxygen on the periodic table, it's in group 16, which means that it has 6 valence electrons. And so 2 plus 6 is 8. We have 8 valence electrons to work with as we draw this structure. Now we have 2 atoms here, or 2 elements, hydrogen and oxygen. There is just 1 oxygen, but there are 2 hydrogens. So oxygen is going to be our central atom. Hydrogen never will be because it can only make 1 bond. Now the convention with Lewis dot structures is that we're going to draw the other atoms above and below this atom and to the left and to the right of this atom. And it really doesn't matter which of those positions we use, they are all equivalent. So I'll draw 1 hydrogen atom up above and I'll draw another one over to the side. It's absolutely equivalent if you wanted to draw the Lewis dot structure where you put them all in a line or you used any 2 positions in here that you wanted. For instance, we could have drawn the oxygen and then drew the hydrogen there and the hydrogen there. All of these will end up being equivalent Lewis dot structures. Our process for putting the valence electrons into the backbone says to start by putting octets on the outside atoms. Well, hydrogen doesn't want an octet. It only wants a duet. It only wants 1 pair of electrons. When we put that pair in, we've got to put it in the bonding position. We have to use it to connect the hydrogen to the central oxygen atom. So we'll put 2 there and we'll put 2 here. And we have now drawn octets on all the outside atoms, duets since it's hydrogen, but we only used 4 electrons. We have 8 to place into this structure, so those 4 leftovers will go on the central oxygen atom. So I'll put 2 here and 2 here, and that uses up all of the electrons. Now to make sure that this is a valid Lewis dot structure, let's start by looking at the central oxygen atom. First, I want to make sure that there are 8 electrons immediately adjacent to that central oxygen, and there are. I'm going to circle those 8 electrons here. So that purple circle that I just drew is showing that there are 8 electrons around oxygen, which is its octet. And then on the hydrogens, hydrogen only wants a duet, and if you look at each hydrogen, it has 2 electrons immediately associated with it. Those bonding electrons get to count both for the octet for oxygen and for the duet for hydrogen. If we were to complete out these other Lewis dot structures that we started, we would still end up with 2 bonding pairs and 2 lone pairs. And all of these structures would be considered equivalent. And then there's one more variation on this that also would be equivalent. I could draw lines in place of the bonding pairs. And so if I do lines in place of the bonding pairs, the bonding electrons would look like that, and then we would still have 2 lone pairs. With lone pairs, we always draw dots. We do not draw lines for lone pairs. For ammonia, I'm going to demonstrate this time around that we can draw the backbone first and then do the electron count. So nitrogen is going to be our central atom, and then we'll place hydrogen in 3 positions. And again, it doesn't matter which 3 positions we use between top, bottom, left, and right. So there's our backbone. For our valence electron count, there is 1 nitrogen atom. It's in group 15, so it has 5 valence electrons. And then there are 3 hydrogens. Each has 1 valence electron. And if we add all of that up, we've got a grand total of 8 valence electrons to place into this structure. Let me just make a quick note right here that that first part of the sum is nitrogen, and that second part of the sum is hydrogen. When we go to put those 8 valence electrons into our structure, we start with octets on the outside atoms. Well, it's hydrogen again, which only wants a duet, so we just want to make sure that those 2 electrons are placed as bonding pairs. That uses 2, 4, 6 of our 8 valence electrons. Those 2 leftovers have to go on the central nitrogen. Now, if we look at the octet on the central nitrogen, we do indeed have an octet of electrons right there. And then if we look for the duets on the hydrogens, each one of these hydrogens has 2 electrons associated with it. So this will be a good Lewis dot structure. Nitrogen trifluoride is our next example. If we find nitrogen on the periodic table, it's in group 15. There's 1 nitrogen atom, and being in group 15 gives it 5 valence electrons. Then we have 3 fluorines, and fluorine is in group 17, the halogens, so it has 7 valence electrons. So if we add this up, 7 times 3 is 21, plus 5 is 26. We have 26 valence electrons to place in this structure. Nitrogen is going to be our central atom when we go to draw the backbone, and then we'll have the 3 fluorines. Now, this is the first time we've drawn a structure where the outside atom actually wants an octet and not just a duet. So we'll start by putting octets on these outside fluorine atoms. That first octet used 8 of our electrons. So we draw our second octet on a fluorine that uses another 8 or 16. And our third octet uses another 8 for 24 electrons total. But our electron count was 26, so I still have 2 left over, and those leftovers will go on our central nitrogen atom. Now, I'd like for you to compare this to the structure that we drew for ammonia on the previous slide. In that structure, we had 3 hydrogens instead of 3 fluorines, and each hydrogen had its octet or its duet. I hope you recognize that these are very, very similar structures. They both have nitrogen in the middle, and what we've done is we've replaced each hydrogen with a halogen, fluorine. We can just, in general, do this. We can take hydrogen with its duet and swap it out with a halogen with its full octet. We can also swap one halogen with another, so we could take out a fluorine and put a chlorine in its place, both with a full octet. The reason we can do this is that they are both 1 electron short of their stable configuration, the duet for hydrogen versus the octet for the halogens. And so they both are going to need to pick up 1 electron from the central atom, so we can just swap them in and out for each other this way. Also, we could generate other structures by swapping out anything for that central atom that's in group 15. So for instance, in place of the nitrogen, we could put something like phosphorus or arsenic because they will all bring 5 valence electrons to the structure. Formaldehyde is the first of our examples that's going to need a double bond. The least electronegative element, the one that's going to go in the center, is the first one shown, which is carbon. And then these other elements will be arranged around it. I'm going to put the oxygen up top and the hydrogens on either side. These are all equivalent positions, so you can arrange them however you would like. For our valence electron count, carbon, there's only 1 of them, and it's going to bring 4. There are 2 hydrogens and each brings 1 electron, and then oxygen's in group 16, so it will bring 6 valence electrons. So if we add the 6 and the 4, that gives us 10, and then we've got another 2 there in the middle. So this is going to be 12 valence electrons that we have to work with. When we go to create our Lewis dot structure by putting the electrons into this backbone, we're going to start with octets on the outside atoms. So there's oxygen, and I'm drawing in its octet. For hydrogen, it only wants a duet, so let's make sure that that's a bonding pair. Now let's see how many electrons we've used. 2, 4, 6, 8, 10, 12. This structure has already used all 12 valence electrons, but there's a problem. Carbon does not have an octet. It only has 6 electrons. That's a problem. We can't leave it this way. The only electrons we have to work with are these lone pairs. Right now, those lone pairs are only counting towards the oxygen's octet, but if we shift them down to be a bonding pair, they will get to count still for the octet for oxygen, but we'll also be able to count them for the octet for carbon. So this is where I was talking in the previous video about you kind of have to show your work along the way. We're not going to immediately draw the correct structure this time, but with just a little bit of revision, we will very quickly arrive at what that correct structure is. So we didn't do anything messing with these 2 outside hydrogens, but we did mess with this outside oxygen. We gave it a double bond to that central carbon, and that still leaves 2 lone pairs on the oxygen atom. Once you start drawing multiple bonds, very frequently people prefer to use the line notation. So an equivalent way of drawing this would be to draw 2 lines connecting carbon to oxygen, and then a single line connecting to each hydrogen, and the oxygen still has 2 lone pairs, and it doesn't matter which positions those lone pairs go in, it's all equivalent. Nitrogen is in group 15. We have 2 nitrogens, each with 5 valence electrons since it's in group 15, which is going to give us 10 electrons to work with. With only 2 atoms, about our only choice for drawing the backbone is to put them side by side. If we start by putting an octet on the outside atoms, well, it's hard to know which one of these should be considered the outside atom, so we'll just pick one. And then that uses 8 of our 10 electrons. I'm just going to put the remaining pair of electrons over there on the other nitrogen. There's a big problem here because that right-hand nitrogen does not have an octet. It only has 4 electrons. You can fix that by moving lone pairs from that other nitrogen in to be bonding pairs. If we move 1 pair in, that right-hand nitrogen now has 6 electrons. So that means we've got to repeat this. Let's take another lone pair and move it in to the middle. And so now, as I redraw that left-hand nitrogen has 1 lone pair left, and it's going to have 3 bonding pairs to the other nitrogen. And then normally people just like to make it look symmetric and show that remaining lone pair on the right-hand nitrogen on the outside. Propane is going to have 20 valence electrons to work with. You can pause this video and add those up if you would like. This being an organic molecule, it has a backbone of 3 carbons, and then each carbon has something attached to it, which is indicated by how this formula is broken up. If we bond the carbons together, that uses 4 electrons. That first carbon has 3 hydrogens attached to it, the second one has 2, and the third one has another 3. And if we bond the hydrogens to the carbons, that is going to use the remainder of these 20 electrons. In this video, we worked multiple examples of compounds that follow the octet rule and how to draw their Lewis dot structures. In the next video, we're going to expand that to look at polyatomic ions and how we have to change the electron count. And then later videos are going to look at compounds that don't follow the octet rule.